All right, welcome to the Neuralink Show and Tell. So we've got an amazing amount of new developments to share with you that I think are incredibly exciting, as well as tell you about the future of what we're planning to do here. It's now this is meant to be a technical podcast, sort of like a. I'm going to provide an overall summary, and then we're going to have a number of members of the Neuralink team come in and give a deep technical overview of the various areas. So yeah, so let me move forward with the overall summary. Now, some of the things I'm going to say are things if you've been following Neuralink, you've already heard before, but for a lot of people out there, they've no idea what Neuralink does, and so I'll be a little bit repetitive of things you may already know, but that others do not. So, the overarching goal of Neuralink is to create ultimately a whole brain interface. So a generalized input-output device that, in the long term, literally could interface with every aspect of your brain, and in the short term, can interface with any given section of your brain and solve a tremendous number of things that cause debilitating issues for people. So. So our long-term is, I'll talk a little bit about our long-term goal. It's going to sound a little esoteric, but it was actually sort of my prime motivation, which was, what do we do about AI? Like, what do we do about artificial general intelligence? If we have digital superintelligence that's just much smarter than any human, how do we mitigate that risk at a species level? How do we mitigate that risk? And then even in a benign scenario where the AI is very, very benevolent, then how do we even go along for the ride? How do we participate? And the conclusion, the thing that the biggest limitation in going along for the ride and in aligning AI, I think, is the bandwidth, the how quickly you can interact with the computer. So we are all already cyborgs in a way, in that your phone and your computer are extensions of yourself. And I'm sure you found, like, if you leave your phone behind, you end up tapping your pockets, and it's like having missing limb syndrome. Like, where the phone is, leaving your phone behind is kind of like a missing limb at this point. You're so used to interfacing with it. You're so used to being a de facto cyborg. So what's the limitation on a phone or a laptop? The limitation is the rate at which you can receive and send information, especially the speed with which you can send information. So if you're interacting with a phone, it's limited by the speed at which you can move your thumbs, or the speed at which you can talk into your phone. This is an extremely low data rate. Maybe it's like 10, optimistically 100 bits per second, but a computer can communicate at gigabits, terabits per second. So this is the fundamental limitation that I think we need to address to mitigate the long-term risk of artificial intelligence, and also just go along for the ride. And yeah. So, but like I said, that's an esoteric explanation that I think will appeal to a niche audience, some of whom may be here. And that's a very difficult problem. So even if we do not succeed with that problem, I think we are confident at this point that we will succeed at many. It's solving many brain injury issues, spine injury issues along the way. So yeah. So anyways. So actually, we have Justin Roiland in the audience. Says, hi, Justin. So it's a little Rick and Morty reference here. This great Rick and Morty episode about intelligence enhancement of your dog, and what's the worst that could happen? So anyway, Rick and Morty, I recommend it. So you want to be able to read the signals from the brain. You want to be able to write the signals. You want to be able to ultimately do that for the entire brain, and then also extend that to communicating to the rest of your nervous system if you have a sort of a severed spinal cord or neck. So. Now this video is now 18 months old. So this is Pager, who is playing monkey mind pong. So this is Pager has a Neuralink implant in this video, and the thing that's interesting is that you can't even see the neural implant. So we've miniaturized the neural implant to the point where it matches the thickness of the skull that is removed. So it's essentially it's sort of like having an Apple Watch or a Fitbit, replacing a piece of skull with like a smartwatch, for lack of a better analogy. So you can see, he looks he's normal. And I think that's pretty important. If you have a Neuralink device, like I could have a Neuralink device implanted right now, and you wouldn't, you wouldn't even know. I mean, hypothetically, maybe one of these demos, in fact, one of these demos I will. Yeah. So yeah. Anyway, so here's I mean, first of all, it's kind of wild. Hey, monkeys can play Pong. They can actually play Pong if you give them a joystick. So Pedro first learned to play Pong with a joystick. So I'm like, that was novel. It's like I didn't know monkeys could play Pong, but they can. And then so we first trained Pedro to play Pong with a joystick. Then we took the joystick away and have the Neuralink, and now he's playing telepathic video games essentially. So what we've been doing since then is we've been on the very difficult journey from prototype to product, and I've often said that prototypes are easy. Production is hard. It's really, I'd say, 100 to 1,000 times harder to go from a prototype to a device that is safe, reliable, works under a wide range of circumstances, is affordable, and done at scale. It's insanely difficult. I mean, there's an old saying that that it's 1% inspiration, 99% perspiration, but I think it might be 99%, 99.9% perspiration. The best example I could give of an idea being easy, but the execution being hard, is going to the moon. It's the idea of going to the moon, easy. Going to the moon, very hard. So, we've been working hard to be ready for our first human, and obviously we want to be extremely careful and certain that it will work well before putting a device in a human. But we've submitted, I think, most of our paperwork to the FDA, and we think probably in about 6 months we should be able to have our first Neuralink in a human. So. But as I said, we do everything we possibly can to test the devices before, not even going into a human, before even going into an animal. So we do benchtop testing, we do accelerated life testing. We have a fake brain simulator that has the texture, and it's like emulating a brain, but it's sort of rubber. And so before we would even think of putting a device in an animal, we do everything we possibly can with rigorous benchtop testing. So we're not cavalier in putting devices into animals. We're extremely careful, and we always want the device, whenever we do the implant, if it's in a sheep or a pig or monkey, to be confirmatory, not exploratory, so that we've done everything we possibly can with benchtop testing, and only then would we consider putting a device in an animal. Yeah, we'll actually show you a demo later today in a few hours, really, of implanting in a brain proxy. And if anyone in the audience wants to volunteer, we have the robot right there. So let's see, and since the page of demo, we've expanded to work with a troop of 6 monkeys. We've actually upgraded Pager. They do varied tasks, and we do everything possible to ensure that things are stable and replicable, and that the device lasts for a long time without degradation. So, and what you're seeing there is, it looks like the Matrix, but that's actually that's a real output of neural signals. So that's not a simulation or just a screensaver or something. Those are actual neurons firing. That is what one of the readouts looks like. And here you can see Sake, it's one of our other monkeys, typing on a keyboard. But now this is telepathic typing. So to be clear, he's not actually using a keyboard. He's moving the cursor with his mind to the highlighted key. Now technically, can't actually spell, and so I don't want to oversell this thing. Because that's the next version. But what's really cool here is Sake the monkey is moving the mouse cursor using just his mind, moving the cursor around to the highlighted key, and then spelling out what we want to spell. But and then so this is something that could be used for somebody who's say quadriplegic or tetraplegic human, even before we make the spinal cord stuff work, is being able to control a mouse cursor, control a phone, and we're confident that someone who has basically no other interface to the outside world would be able to control their phone better than someone who has working hands. So. Yeah. And I mentioned upgradability. Upgradability is very important because our first production device will be much like an iPhone 1, and I'm pretty sure you would not want an iPhone 1 stuck in your head if the iPhone 14 is available. So it's going to be be able to demonstrate full reversibility and upgradability, so you can remove a device and replace it with the latest version, or if it stopped working for any reason, replace it. That's a fundamental requirement for the device at Neuralink. And I should say both Sake and Pager were upgraded to our latest and greatest implants. That's been really over a year and a half now that Pager's had for the first implant and then the upgraded implant. So this is a very good sign that it lasts for a long time with no observed ill effects. I think it's also important to show that Sake actually likes doing the demo. And is not like strapped to the chair or anything. So the monkeys actually enjoy doing the demos because they get the banana smoothie, and it's kind of a fun game. So I guess what I'm trying to make is like we care a great deal about animal welfare, and I'm pretty sure like our monkeys are pretty happy, you know. So as you can see, a quick decision maker on the fruit front. So for the first two applications we're going to aim for in humans are restoring vision, and I think this is like notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision. Because the visual part of the cortex is still there. Even if they've never seen before, we're confident that they could see. And then the other application being in the motor cortex, where we would initially enable someone who has no ability, almost no ability to operate their muscles, you know, sort of like a sort of Stephen Hawking type situation, and enable them to operate their phone faster than someone who has working hands. But then obviously even better than that would be to bridge the connection. Take the signals from the motor cortex, and let's say somebody's got a broken neck, then bridging those signals to Neuralink devices located in the spinal cord. So we're confident there are no physical limitations to enabling full body functionality. I mean, as miraculous as it may sound, we're confident that it is possible to restore full body functionality to someone who has a severed spinal cord. So, yeah. All right. And then I want to emphasize again that the primary purpose of this update is recruiting. A lot of times people think that they couldn't really work at Neuralink because they don't know anything about biology or how brains work. And the thing that we really want to emphasize here is that you don't need to, because when you break down the skills that are needed to make Neuralink work, it's actually many of the same skills that are required to make a smartwatch or modern phone work. So it's sort of, software, batteries, radios, inductive charging, and as well as things that are specific to us, like animal care and clinical and regulatory matters. Obviously, machine learning, that phrase is used a lot. But we obviously need to interpret the signals from the brain, which is a biological neural net, and the best thing to interpret a biological neural net is a digital neural net. So this is, if there's one message I want to convey, it is that if you have expertise in creating advanced devices like watches and phones, computers, then your capabilities would be of great use in solving these important problems. That's more than anything the message I want to convey. Let's see. Yeah. So with that, I guess DJ. So DJ's was on the founding team of Neuralink and has made immense contributions to the company, as have many of the others who will present. But I want just to thank DJ for his immense contribution to Neuralink. And all right, cool. Thank you.
Thanks, Elon. When I moved from South Korea at age 13 and needed to learn a new language to communicate, I wondered whether there are better and more effective means of communicating my thoughts to the outside world. And watching Neo learn Kung Fu in The Matrix, I remember thinking, wow, I want to work on that, work on making that possible. And today, I believe that this is a tractable engineering challenge. Since everything about your intentions, your thoughts, and your experiences are all in your brain, encoded as firing statistics of action potentials, if you're able to put electrodes in the right places with the right sensing and stimulation capabilities, this and many other applications that Elon talked about are possible, and we can help a lot of people. I'm incredibly excited to be working on this ambitious yet important mission to make that future a reality here at Neuralink. And I'm also incredibly honored to be working with some of the brilliant colleagues, scientists and engineers across many engineering disciplines, to work on this intersection of biology and technology. You'll hear from several of them today to learn about the breadth of technical challenges we face and our progress in the last year. And I think you'll find that for most of these challenges, as Elon mentioned, you don't need a prior understanding of how the brain works, and that a lot of what we do is applying engineering first principles to biology. So how do you create a high bandwidth generalized interface to the brain? From day one, we focused on a set of foundational technologies that are safe, scalable, and capable of accessing all areas of the brain. These three axes, safety, scalability, and access to brain regions, really form the basis for how we engineer products here at Neuralink. Safety, because we want to make our devices as well as the installation as safe as possible so that we can drive the adoption of this technology. And scalability, because as we make our devices safer and more useful, more people will want it. And with scale, we also want to make it more affordable. And access to brain regions so that we can expand the functionalities of our technologies. So our first steps along these dimensions for our device is what we call the N1 implant. It's a size of about a quarter, and it has over 1,000 channels that are capable of recording and stimulating. It's microfabricated on a flexible thin film arrays that we call threads. It's fully implantable and wireless, so no wires, and after the surgery, the implant is under the skin and it is invisible. It also has a battery that you can charge wirelessly, and you can use it at home. So similarly, for implanting our device safely into the brain, we built a surgical robot that we call the R1 robot. It's capable of maneuvering these tiny threads that are only on the order of few red blood cells wide, and inserting them reliably into a moving brain while avoiding vasculature. It's quite good at doing this reliably. And in fact, because we've never shown an end-to-end insertion of a robot in action, we're going to do a live demo of the robot doing surgery in our brain proxy. So who wants to see some insertions? So here it is. That's our R1 robot with our patient Alpha, who's lying comfortably on the patient bed. This is what we call the targeting view. So what you're seeing is this is a picture of our brain proxy. And the pink represents the cortical surface that we want to insert our electrodes into. And the black represents the vasculatures that we want to avoid. And what you're seeing is these hash marked with numbers that represents where we intend to put each of our threads. So should we see some insertions? So this is another view real quick. On the left is the view of the insertion area. And on the right, what the robot's going to do is it's going to peel the array, the threads, one by one from its silicon backing and insert it into the targets that we predetermined in the targeting view. So there you go. That's the first insertion. So we're going to see a couple more insertions. The whole process of inserting about 64 threads in our first product is going to be around 15 minutes for this robot. So yeah, there's a second one that went in, and we're going to do a third one. There you go. And then that's going to go in the background, and we'll come back to it in the later part of the presentation. And as Elon mentioned, we've been working very hard to go from prototype to building product. As part of this, one of the things that we did is to move our device manufacturing to a dedicated facility in Austin for scale-up manufacturing. And what's important to highlight, and is evident in this clip, is that it's very typical for us to have our engineers who design also work on the physical manufacturing line to build and debug. And this has been extremely, extremely critical in reducing our iteration cycle time. And we've also scaled up our surgery. So we now have a dedicated, our own OR, in fact, a double OR in Austin. And this is just a stepping stone before we eventually build our own Neuralink clinic. So with this product, N1 and R1, our initial goal is to help people with paralysis from complete spinal cord injury regain their digital freedom by enabling them to use their devices as good as, if not better, than they could before the injury. And as Elon mentioned, over the last year, this has been the central focus of the company. And we've been working very closely with the FDA to get approval and to launch our first in-human clinical trial in the US, hopefully in the next 6 months. So hopefully this gives you a good overview of our product. For the next hour, we're going to go through a deep technical dives on these topics to tell you about our technical challenges, share some of our progress, and preview what's coming next. So with that, over to Nir from my team, who's going to talk to you about neural decoding.
Thank you, DJ. And hey, everyone. My name is Nir Evan-Chen, and I'm the head of Brain Interfaces Applications. Our goal is to enable someone with paralysis control a computer, as well as me, or even better. We'd like to provide fast and accurate control with all the functionality of computers that works anytime, anywhere. So I'm very excited to show you how we're using the N1 device with our software and algorithms to achieve this. Last year, we shared with you a video of Pedro the monkey controlling a computer cursor with his brain. So how do we do that? Just a brief reminder. First, we record his neural activity from the motor cortex using the N1 device. We can record from over thousands of channels while he's playing with the joystick. Then we can train a neural net that predicts the cursor velocity from the patterns of his neural activity. With this decoder, he can then control a cursor just by thinking about it, without even moving the joystick. He can play with this decoder a variety of games, also a grid task, where he's moving the white dot towards the yellow target. Every time he gets one, he receives a drop of his favorite smoothie, and he chooses to play this game every day. Here you can see his performance from early 2021, around the time we released the previous demo. It's quite accurate, but it's a bit slower than what we would like. And cursor control is the foundation for interacting with most computer applications. So since then, we've been working to improve cursor speed and accuracy. As you can see, it's much, much faster, almost twice as fast. Yeah. However, it's still a bit slower than what I can do. So we are working on creative ways to improve that. Now, speed is not enough. You want a full set of functionalities. And for decades, most software was built for mouse and keyboard control. And it doesn't make sense to reinvent this entire ecosystem for brain control, at least for now. So we are working and we are designing mouse and keyboard interfaces for the brain. The way we do that is by training Pedro and his friends on a variety of computer tasks, and then designing algorithms to predict their behavior. Here you can see a few examples of tasks in different phases of monkey training. For example, left and right click, click and drag, cursor typing, swipe typing, handwriting, and even hand gestures. Now, interacting with computer is bidirectional, and feedback is very important. Unlike when I click on a button and I can physically feel the button being pressed, when a potential N1 user will attempt to click, they won't be able to feel it. An example of how we are addressing that is by providing a real-time visual feedback that represents the strength of the neural click by changing the color of the cursor. Just by typing on a physical keyboard is much faster and easier than typing on an iPad keyboard. This will make the brain control much faster and easier to use. Typing, one of the most important functionalities. So you already seen this message, and I want to show you the behind the scene of how this message was created. And here you can see again Saki using the virtual keyboard, typing this message. This virtual keyboard is similar to the one I use on my phone. And with the speed and accuracy that we achieved so far, typing on a virtual keyboard is already fast and easy. However, I never use a virtual keyboard when I type on my computer, because it covers my screen, and it's also much slower than what I can do with my 10 fingers. We can do better. For example, a group from Stanford asked a person to imagine handwriting letters. Then they decoded the letters from his brain activity. Using this approach, they were able to speed up the typing rate. We started this project with our monkeys, but of course they don't know how to write. So to mimic writing, we trained Ranger, one of our favorite monkeys, to trace digits on an iPad. Here you can see him tracing the digit 5 and the digit 2. Then we recorded his neural activity with the N1 device. But now, instead of decoding the cursor velocity, we decode in real time the digit that he's tracing on the screen. We had two main takeaways from this project. One, that monkeys are awesome and can learn very, very complex tasks. The second one, that although it can increase the typing rate, it requires hundreds of examples and samples of each of the digits and the characters we wanted to classify. This would not scale. The way we are solving that is by indirection. Instead of decoding directly the digits, we first decode the hand trajectory of on the screen. And then, when we decoded the hand trajectory, we can use any off-the-shelf handwriting classifier to predict the digit and the characters. For example, classifiers that are trained on an MNIST dataset. Why it's so important? It's important because now we can potentially decode any character in any language with only one neural decoder for hand trajectory. It means that you can write in English, Hebrew, Mandarin, or even monkey language, and we can understand you wanted a banana. So there are many challenges ahead of us to improve functionality and speed, and I want to hand it off to Bliss to talk about the third part, how we are making our brain interfaces work anytime, anywhere.
Hello, everyone. My name is Bliss, and I'm a software engineer here at Neuralink. When I use my computer, my mouse and keyboard work how I intend them to, at least like 99.9999% of the time. My goal is to enable a user with paralysis to control their computer as reliably as I can. Here's what we want that experience to feel like. In this video, you can see Saki walking over to his MacBook and choosing to work on his typing task. The entire decoding system works out of the box, and it feels totally plug and play. The first step to achieving this kind of high reliability is to test extensively offline. A typical flow for using the N1 link is to connect over Bluetooth, stream out neural activity from the brain, and then use that neural activity to train decoders and do real-time inference. We've built a simulation for exactly this sequence, but instead of using a monkey with an implant, we use a simulated brain that injects synthetic neural activity into an implant sitting in a server rack. From the point of view of that implant, it's in a real brain. This simulation runs on every code commit to validate that from the hardware all the way up through to the neural decoders, our entire stack can achieve state-of-the-art performance. However, while this kind of simulation is great for integration testing of software and hardware, it's not yet detailed enough to guarantee high reliability in the real world. In the real world, the underlying signals we're trying to decode actually change day to day. In this plot, you can see the average firing rate detected on a representative channel of Saki's implant. Each bar represents one day, and you can see that each day has a different average firing rate than the previous. This presents us with a very interesting problem for how to make our decoders robust day to day. It can actually happen that if you train a neural decoder on one day of data and then try to use it on the next, the average firing rates can actually shift enough to cause a bias in the output of the model. Here on the right, you can see that this bias is making it hard for the cursor to move to the upper right corner. You see it struggling here to make it up to the upper right, and then it moves much more effortlessly down to the bottom left. We're trying many approaches to mitigate this problem. Some examples include building models on large data sets of many days of data to try to find patterns of neural activity that are stable across days. Another approach we're trying is to continuously sample statistics of neural activity on the implant and use the latest estimates to pre-process the data before feeding it into the model. This is really an active area of research for the team, and it's a critical problem to solve if we want to enable someone with paralysis to control their computer as well as I can. Another big problem we have is to minimize the time it takes for a spike in the brain to impact the movement of the cursor on the screen. If you have lag or jitter in this control loop, the cursor becomes hard to control, leading to the kinds of overshoots that you can see here on the right. One big improvement we've made towards in this direction is called phase lock. Phase lock aligns the edge of each packet that we send off the implant to the exact moment that the Bluetooth radio is going to wake up. This minimizes the time it takes for a spike in the brain to be incorporated into the prediction of our neural network. Here you can see the latency distribution after phase lock. Not only has the mean been greatly reduced, but the variance has been reduced as well. This makes it easier for the user to predict the behavior of their cursor. Over the last year, we've made tremendous improvements to the stability and reliability of our system. And we've been able to demonstrate consistent high performance across many sessions and many months. However, there's still a long road ahead of us before this system will truly feel plug and play. So if solving the hard problems required to ship this technology is exciting to you, you should consider applying to join the team. Now, I'm going to hand it over to Avinash to talk about how our custom low-power ASIC detects spikes in the brain.
Hi, I'm Avinash, one of the engineers on the ASIC team. We designed the custom neural sensors, which include both analog and digital circuitry, to record and stimulate across 1,024 independent channels. We faced challenges across all three major metrics: performance, power, and area. Not only do we have to fit all 1024 channels into a single quarter-sized implant, but we also have to measure spiking activity less than 20 microvolts in amplitude. And today, I'd like to focus on the last challenge I mentioned, power. Power consumption is important to us because we want to give future users a full day of use of their implant without any interruption for charging. Back in 2018, we were sending every sample from every channel off the device for processing, which burned a ton of power. In 2020, we brought spike detection onto the chip. As you may know, neurons transmit information by firing. So simply monitoring for these spikes and only sending these spike events off the implant acts as a very efficient form of compression. And over the past 2 years, we've continued to make optimizations within the ASIC, dropping the total system power consumption down to just 32 milliwatts and doubling battery life. Let's take a look at our on-chip spike detection algorithm, which makes our battery-powered implants possible. We first start by applying a 500 Hz to 5 kHz bandpass filter to remove noise that's out of band. Next, we use an estimate of the noise floor to generate an adaptive threshold per channel. And finally, our spike detector module identifies 3 key points of a spike. Identifying 3 points allows us to detect not just the presence of a spike, but the shape of a spike as well. This can be extremely important for distinguishing between multiple neurons adjacent to a single channel. Today, I'd like to focus on one of the many optimizations that we've made in our latest chip. This one specifically cutting system power by 15%. Note that neurons spike relatively infrequently, which means that our spike detector spends a lot of time searching for the first point of a spike and very little time searching for the other 2 points of a spike that only occur after the threshold is crossed. We can use this characteristic of the input waveform to reduce memory accesses within the chip by 30%. Let's take a look at how that works. Our spike detector is implemented as a single functional unit that's shared across all channels with an SRAM to buffer the state of each channel. As a sample comes in, its channel state is read from SRAM, an incremental spike detection step is run, and then the updated state is written back to SRAM. Since this is happening 20 million times per second across the implant, each of these accesses add up quite quickly. In our latest chip, we split the state into 2 parts, a hot state and a cold state. The hot state is accessed on every cycle, while the cold state is only accessed once the threshold is crossed, reducing the average access width and saving power. We're also working on a next-generation stimulation-focused chip with 4,096 channels still within the footprint of our current chips. In addition to increasing the channel count, we're also increasing the drive voltage so we can get better activation per channel. And to support this higher channel count, as well as a broad range of future applications that you'll soon hear about, we're adding an ARM core onto the chip. And finally, since these chips are the same size as our current chips, we can still put 4 of them together into a single implant for a total of 16,000 channels still within the size of a quarter. As you can see, we've been working very hard to improve the power consumption within the implant, but we've also been working very hard to improve the charging experience of the implant, which Matt will talk about. But first, the robot has just completed inserting all 64 threads, so let's take a look. This is a view of the insertion site, similar to the one that DJ showed you earlier. But instead of the targeting reticles, if you look closely, you can see that all 64 threads, each carrying 16 electrodes, have been inserted into the brain proxy while avoiding vasculature, and all just within the past 20 minutes. Let's hand it over to Matt now to continue the technical deep dive.
Hi, I'm Matt, head of Brain Interfaces Electrical Engineering. Our fully implantable N1 device depends on a battery for continuous operation. When that battery is running low, charging is accomplished through wireless power transfer. However, unlike many consumer electronic devices, which can simply offer a physical connector, charging a fully implantable device poses several unique challenges. First, the system must operate over a wide charging volume without relying on magnets for perfect alignment. The system must be robust to disturbance and complete quickly so as not to be overly burdensome. However, most important is safety. In contact with brain tissue, the outer surface of the implant must not rise more than 2 degrees C. In pursuit of these goals, our charging system has gone through several engineering iterations. The first, if you watched our pig demo in August of 2020, Gertrude was implanted with a version of the N1 charged with our first generation charger. This device was implemented in a small puck package and later separated into a remote coil and battery base. This charger was challenging to use. However, we learned a lot through its implementation. Our current production charger, which charges our current generation of implants, is implemented in an aluminum battery base, which also includes the drive circuitry. A remote coil, 4 times the size of our original device, also disconnectable. This remote coil has increased switching frequency, driving improved coil coupling. This charger is in use today, including several applications within our engineering and animal test facilities. I'd like to show you one of these applications here with a device we call our simple charger. And the coil has been embedded into the habitat. With the addition of one new outer control loop plus a banana smoothie pump, the troop has been trained to charge themselves. So let's see how Pager charges his implant. On the right, we're streaming real-time diagnostics from Pager's N1. When he climbs up and sits below the coil, you can see the charger automatically detect his presence and transition from searching to charging. We see the regulated power output on a scale of 0 to 1 and the current driven into his battery. I mentioned earlier that we improved the coil coupling. However, the high quality factor coils exhibit good charging performance over relatively larger distances, but as they're brought closer to the implant, what you see is a peak splitting effect, where the best, highest efficiency power transfer is pushed up into higher frequencies outside of the ISM band, required for compliance with regulated radiated emissions. In our next generation charger, we address this problem by the introduction of dynamic tuning, shown on the right. This allows us to, in real time, adjust the resonant frequency of the transmit and receive coils so that we can change their properties just ahead of degraded performance. The electrical engineering team is currently engaged in developing a 3rd generation charger. Notable improvements include bidirectional near-field communication. This has allowed us to reduce the control latency and improve the thermal regulation. Improved thermal regulation results in faster charge times. And now, Julian will tell us about how we test the N1.
Thank you very much, Matt. My name is Julian, and I lead the embedded software group on the Brain Interfaces team. So when we started building implants, we had a small manufacturing line, and to collect data from an implant, you would manually walk over with your laptop, you would connect and collect the data of interest. But our goal is to make an ultra-safe and ultra-reliable implant. And so to do this, we scaled up the manufacturing line, our testing throughput, and data collection capabilities. So firstly, we added a large suite of acceptance tests to the manufacturing line. These test the functionality of each component and the final assembly. Implants coming off the line are then subjected to benchtop testing, accelerated lifetime, and animal models. We then collect data from these implants round the clock. This data is processed by a series of cloud workers and displayed in an aggregate manner. And then finally, all of this information feeds back into our design process and empowers our engineers to answer any question about any implant at any time. I'm now going to walk you through different parts of this infrastructure, starting off with firmware testing. So the implant contains a small microprocessor running firmware to manage a whole bunch of its operations. And before we release a firmware update, we want to rigorously test it with both unit and hardware-in-the-loop tests, also known as hill tests. So to do a hill test, what you do is you instrument the battery, you instrument the power rails, the microprocessor, and then we connect to each device with a Bluetooth client. And then we walk the devices through various scenarios to test things like power consumption, real-time performance, security systems, fault recovery mechanisms, a lot of different things. In our original implementation of these systems, we used off-the-shelf components to start automating tests quickly. However, these systems were constructed in a relatively artisan fashion and were very difficult to maintain. And this meant that testing quickly became the bottleneck for development. So to alleviate this, the hardware and software teams developed a new system which integrates all the required components onto a single baseboard. We can then put the charger and implant hardware on individual modules that plug into this baseboard, including one board with opposing coils so that we can test charging performance. This architecture allows us to rapidly iterate different hardware prototypes because we can simply drop them into this system and reuse all the testing infrastructure. Additionally, we can host the current and next generation of our neural ASICs onto FPGAs and plug those into this board as well. And that allows us to test a whole extra layer altogether. So that's how we generated this rather inceptive image here on the right. What you're looking at is spiking activity emitted from some of our simulated neural sensors, streamed through the entire system over Bluetooth, and then displayed on a phone. This allows us to test everything in one system from chip to cloud. This system is 1/5 the cost, 1/5 the volume, and is very easy to manufacture. This allows every developer to have a personal unit on their desk, and it also allows us to shard the entire test suite over a large number of these units mounted into a rack. All of this has greatly accelerated our rate of development. Let's look next at how we monitor the implant's electronics, the battery, and the enclosure. So the implant will periodically capture all of its vital signs and commit those to flash. And then upon next connection with one of our recording stations, it will stream that data off. So for instance, if we look at humidity, we can get an understanding of the integrity of the implant's enclosure. And by looking at battery voltage and power measurements, we can gauge battery health. All of this is done automatically without any intervention, giving us 24/7 visibility into the quality of every single device. Additionally, we can use this infrastructure to request high fidelity information on demand so that we can investigate different anomalous situations. So for instance, in this particular scenario, we were trying to track down the source of some spurious spikes that we were observing on different channels, and so we requested raw wave samples directly from those channels. Capturing good quality neural signals requires intact, low impedance electrodes. And so this is also something we monitor very closely with dedicated circuitry on the neural sensor. So how do we do this? We do this by first using an onboard DAC to play a test tone on a single channel. And then we record, using our ADCs simultaneously, we record the response signal on both that channel and physically adjacent channels. Not only can we measure the impedance of every channel with this, but we can also map different physical phenomena to different characteristic signatures. So for instance, an open channel will appear as a very large response on the channel, and shorter channels will appear as a large response on neighboring channels. By looking at the purity of the signal coming back, we can also validate that the analog front end of the neural sensor itself is operational. In our original implementation of doing these impedance scans, it took 4 hours to get through all 1,000 channels. But by parallelizing the tests, downsampling, filtering, and then reducing the amount of information we have to stream off the device by moving a lot of the calculation to the firmware side, we're now able to scan all 1,000 channels in just 20 seconds. This means that we can run impedance on every implant every day. And then our internal dashboards can play back a history of this impedance so that we can get a really good quantitative insight into that interface between biology and electronics. Now that you have an idea about how we test and monitor our implants, I'm going to hand it off to Josh, who's going to tell you about how we get feedback even faster by accelerating our implants to failure.
Hello, my name is Joshua Hess, and I'm an engineer on the Brain Interfaces team. We are responsible for the implant system design, as well as many of the manufacturing and testing tools. Julian just talked to you a little bit about some of the ways in which we test our implant electronics hardware and software. But what about the entire system as it relates to longevity in tissue? One of the ways we've addressed this is with the development of our in-house accelerated lifetime testing system. The system allows us to expedite and capture long-duration implant failure modes at scale to rapidly increase our pace of iteration. Even better, the system also significantly reduces the amount of tests which require animal models, both for implant prototypes and, of course, longevity testing. So how does the system work? Well, at a very basic level, it comes down to three things. First, we want to mimic the internal chemistry of tissue. Next, we want to accelerate these chemical interactions as well as diffusion with our implant materials. And finally, we want to aggressively cycle the internal electronics of our implant. With these things, primarily the first two, we have achieved a conservative 4x acceleration factor by the Arrhenius relationship. In other words, every day our implants spend in our accelerated system is equivalent to at least 4 days spent in vivo. Historically, one of our greatest challenges has been the battle against moisture ingress into our implants. So we continuously monitor the internal humidity to watch for abnormal rise. Here, in white, you can see some internal humidity data from implants in some of our animals for the duration of over 1 year. As you can see, our internal humidity sensing is so sensitive, it can even detect the very small and slow humidity rise just from diffusion through our implant materials. Now, in blue, you can see that same internal humidity data, but from devices in our accelerated system. Now, if we adjust this data for our acceleration factor, you can begin to see not only the agreement in this data, but also just how far into the future this data extends. Now, in red, you can see a device which has failed in our accelerated system. This device showed an abnormal increase in humidity over the duration of many months before implant electronic failures occurred. So how do we build this system? Well, we started building the first system prototype just after the COVID shutdown had begun in early 2020. So we had to get a little creative. As you can see, our first system prototype was a little scrappy and operated out of one of our apartments, as indicated by the carpeting. Although scrappy, the system allowed us the fastest path to start testing our devices, tuning our working fluid chemistry, and checking our constraints. We also immediately started root causing observed failures in early implant prototypes, fed that information into the next prototype designs, and literally rinsed and repeated. Over the duration of just a few months, the system was built out totally custom and highly iterated with 2 system versions and countless minor iterations, leading us to our currently operated 3rd generation system, which achieves high density testing with automatic in-vessel charging as well as automatic data collection. The system also features an implant sled assembly, which accepts brain proxy material such that the implant can be installed and inserted by the surgical robot, just like you saw a few minutes ago. We also integrated the system into a high-density rack mount form factor, along with a centralized fluid management system, both for chemical uniformity across vessels and also reduced operational maintenance. The system has been in operation for the last 1.5 years and has had its fair share of challenges. Since the system itself is undergoing the same accelerated abuse as the implants within it, it has been extremely challenging to design, build, and maintain a system of this scale while keeping it robust, even against itself. So what comes next? Well, we have started work on our 4th generation system and have totally redesigned it from the ground up to be a hot swappable, single implant per vessel design, partly inspired by high density compute servers. With this new system, we will achieve a whole new level of density, robustness, and scale. We also intend to have many of these systems operational in the pursuit of capturing even the lowest frequency edge case failure modes. With this, we will have thousands of implants testing in pursuit of these goals. We've already started work building out this system, but there is still a lot left to do. There are also many exciting challenges ahead of us, such as introducing mechanical stressing, brain proxy micromotion, and even replicating tissue growth around the threads for more complete and representative accelerated testing. So now that you've heard some of the ways in which we rigorously test our implant designs before production for surgery, Christine is now going to take you through a detailed look at our surgical process.
Thanks, Josh. Hi, everyone. I'm Christine, lead of the surgery engineering team. To get an N1 device, it's essentially these steps: targeting and the incision, drill the craniectomy, remove the tough outer meningeal layer called the dura, then insert the thin, flexible threads of electrodes, place the implant into the hole we created, and then that's it. You've got an implant under the skin. Look, Ma, no wires. Just kidding. I mean, seriously, no wires, but I don't actually have one. The surgical robot does the thread insertion part of the surgery. This is because it would be very difficult to do manually. Imagine taking a hair from your head and trying to stick it into Jell-O covered by saran wrap, and doing this at a precise depth and position, and doing this 64 times within a reasonable amount of time. And a neurosurgeon would probably not like it very much if we asked them to do this for the surgery. So we have the robot that you saw doing its tiny dance. I sort of wanted to call it Tiny Dancer, but it's called R1, which is also great. The rest of the surgery is done by the neurosurgeon. In order for us to make an accessible and affordable procedure, we need to revisit this. I'll tell you why. When I was in school, my dad lost the ability to walk and to use his arms and even to speak. He was diagnosed with ALS. We would look on the internet and you could see maybe one person here or there who had some cool custom robotic assistive device, but it was deeply frustrating how limited were the options available to him. And there's hundreds of thousands of people with paresis, not even counting people with other conditions that our device might be able to help. Meanwhile, there's not that many neurosurgeons, maybe about 10 per million people. And it takes about a decade or more to train a neurosurgeon, and they're already generally very busy. And as you can imagine, their time is very expensive. So in order for us to do the most good and have an affordable and accessible procedure, we need to figure out how one neurosurgeon could oversee many procedures at the same time. This might sound sort of crazy, but probably so did laser eye surgery before LASIK made it normal. LASIK's been around for about 30 years and counting. In the beginning, the laser robot did just the most fundamental core part that it had to do, and the surgeon did the rest. And over the iterations, the surgeon has to do less and less, and the laser robot does most of it. And it's a highly compelling procedure. It takes just a handful of minutes and often gives life-changing results. Since I joined in 2017, we've also done a handful of iterations to optimize the thread insertions of the robot. One of the challenges that we've had to face has to do with the optomechanical packaging. So as you can see here, there's about 3 primary optical paths that are really valuable for us to have reliable thread insertions. One is the visible imaging of the needle inserting the thread. And then another is the laser interferometry system called OCT, optical coherence tomography, that gives us the precise position of the brain while it's moving in real time. And then also we have to provide lighting and illumination to see what's going on in the visible light camera. And doing all this where the needle is at the bottom of the craniectomy, especially when it's close to the skull wall, can be pretty difficult to fit everything and be able to see it. So the way that the team solved this is by putting all 3 of these optical paths into one optical stack using photon magic or polarization, whatever you want to call it. And that enables us to do vessel avoidance in real time. So as I mentioned, the brain is moving. And where we place targets in the beginning may not be where you want to insert at the moment the needle is going down there. So the robot can actually detect the vessels and then determine if we're going to insert onto a vessel or not, if it's safe to insert. And then that way we can avoid inserting onto major vessels. And that brings us to the robot that we have here today. There's still a lot for us to do to get to that procedure where we reduce the role of the neurosurgeon and make it affordable and accessible. The two elements of the surgery that demand the most skills from the neurosurgeon are the craniectomy and the directomy. Alex and Sam are going to tell you a bit more about how we think we can get rid of the directomy step. So that leaves the craniectomy. In neurosurgery, if your craniectomy is small enough, you can use a standard tool called a perforator, which makes quick work of this job. But for a larger craniectomy, the surgeon has to rely on their skill in order to accommodate the variability patient to patient in skull thickness, skull hardness. Even within the same patient, in the same craniectomy, you can have different skull thicknesses, for example. In addition, if we can make something that has a very high precision craniectomy, we can open the design space for future ways of mounting the implant to the skull. So I'll show you a few of our prototypes. Ultrasonic cutters, like what's on the screen, and oscillating cutters have the benefit of not cutting soft tissue. You can cut the bone and not the brain. But however, as you can see here, our ultrasonic cutter prototype created quite a bit of heat to cut at the rate that we wanted. So onto the oscillating saw. Here, we designed a blade to minimize cut time and also conducted sound and also heating. And as you can see, you can cut through hard things like bone, but not soft things like skin. It's simple and it works. However, if you wanted to cut an arbitrary depth or arbitrary shape, the oscillating saw just won't cut it. I was afraid no one would get it. You guys are smart. There's a time-tested solution for drilling arbitrary shapes, which is a CNC drill. The challenge with us doing this on a person is that we need to make sure it cuts reliably every single time, doesn't cut too deep. And a few ways that we're using feedback to make sure we don't cut through the brain are force feedback and also impedance. And if I could get a volunteer, no, just kidding. Maybe next time. But yeah, so this is some insight into some of the things we're working on to make an accessible and affordable procedure. And now Alex is going to tell you a bit about our next generation developments.
Thanks, Christine. I'm Alex. I'm a mechanical engineer here on the robotics team. Now that we've covered the technology and surgical process for our current device, we'd like to cover some of our next generation development projects. I and the next couple speakers would like to talk about one of those projects, which is enabling device upgradability. You've gotten to hear about the advancements we've made over the past year. We've improved implant robustness, battery and charging performance, Bluetooth usability. Realistically, every new device version is going to be significantly better. It'll be more functional, it'll last longer. We need to keep this new technology accessible for our early adopters. This means that we need a solution to make device upgrade or replacement just as easy as it is to initially install. As many medical device companies have found, this is a challenging problem. The body's healing response doesn't make this easy, so this isn't solved yet. But we've made significant progress towards enabling this that we'd like to cover today. Now, we'll have to start with some background as to what makes device upgrade challenging. And we'll start with the anatomy. Under the skin, you have the skull. Below that, the dura, a tough membrane that separates the bone from the brain. And between the dura and the brain, you have the pia arachnoid complex, a fluid-filled suspension for the brain. To install the device, the surgeon removes a disc of skull and dura to expose the brain surface. The device then replaces the removed material. The challenge is here at this interface. Over months, all empty volume is filled by tissue, encapsulating the device and the threads. The device would be trivially easy to remove. Because of the thread's small size, they would slip right out of the brain. It's the tissue layer that forms above the surface that makes removal challenging. We've built tools in-house to study this response and characterize it, such as histology and micro-CT. In these images, you can see that layer of tissue that has formed above the surface, encapsulating the threads and adhering to the surrounding tissue. We've explored many different avenues for designing around this healing process and finding a solution to make device upgrades seamless. Our best successes have come from making the procedure less invasive. Instead of directly exposing the brain's surface, we instead keep the dura in place, maintaining the body's natural protective barrier. This prevents encapsulation at the brain's surface. And really, this is actually a huge win for making the surgery simpler and safer, as Christine alluded to. However, this doesn't come for free. The dura is a very tough, opaque membrane. As you can see in these SEM images, it's composed of a dense network of collagen fibers. These offer an array of technical challenges for inserting our electrodes. One of those challenges is imaging through the dura. As you can see on the left, our current custom optical systems offer pretty incredible capabilities for imaging the exposed brain surface. However, as you can see on the right, once the dura is in place, you can't see the dense vasculature at the brain surface. The dura is in the way. There's simply too much attenuation. To solve this problem, we're developing a new optical system that uses a medical standard fluorescent dye to image vessels underneath the tissue. Here, you can see that dye perfusing through the vessels, highlighting them. There's still a lot of engineering work to go to prove accuracy and repeatability of this system, but once that's done, this will allow us to target and avoid blood vessels underneath the dura. We're also exploring applying our laser imaging system to deeper tissue structures. In the bottom left, you can see a section of the tissue layers underneath the dura. This image is compiled from multiple volumes from our optical coherence tomography system. You can see the collage of those volumes above. In the future, these new systems, when combined with correlation to pre-op imaging, such as MRI, will enable precise targeting without directly exposing the brain surface. Now, imaging isn't the only challenge that comes with the tough dural anatomy. Now, I'd like to hand it over to Sam to talk about some of the challenges of inserting our electrodes through this membrane.
Thanks, Alex. Hey, I'm Sam, and I lead the needle manufacturing and design team. So, as Alex mentioned, the same properties of the dura that make it a good protector of the brain also make it really difficult for us to insert the threads into. In humans, the dura can be over 1 millimeter in thickness, which doesn't sound like a lot, but compared to our 40-micron needles, it actually is a lot. For example, if you scaled up the needles to the size of a pencil, the dura would scale to over 4 inches in thickness. Take a look at how far you have to zoom in to even see it. By the time the features of the needle come into frame, you could see individual red blood cells in the same frame. This is just wait. This is a real-life SEM image of our latest design. On the left there, you can see the end of the thread. In the middle is the needle, and on the right is actually a piece of my hair. So yeah, it's extremely small. And besides being really small, there's a lot of other challenges associated with designing this. One challenge is that we have to use the needle and the protective cannula that it sits in to grab onto the thread and to hold it while we peel it from this protective silicon backing. And then we have to keep holding it while we bring it over to the surface and then release it from the cannula during insertions.